Okay, we're now recording. Let's get the slideshow set up from current slide, and we'll pick up. Now, I'm pretty sure we did this slide last time, okay? Any questions on this or any questions on anything? I did finish late last night. I hope there aren't too many typos in it, working out your test. So any questions for, pass those out as soon as we finish this section 11.2. All right, no questions on this either. So we pick up next, in physics, we often describe a path of a particle moving with constant speed along a circle of radius r in terms of the constant, we said constant speed, along a circle of radius r. So it's going with constant speed. That also means it has a constant angular velocity. The angular velocity is typically given the symbol omega. So to describe a particle moving along at a constant speed along a circle's radius r, capital R, with a constant angular momentum, angular speed omega. Sorry. Oh. Don't get started this early. C of t, this is the motion along this circle, radius r, and constant, this is an angle here, and the rate at which the angle is increasing is omega. So this would be r, the radius. Well, they write it this way. I would have written it otherwise. Cosine omega t, r sine omega t. Oops, left off my t. Okay. Now, okay, the constant omega is called the angular velocity, I already said. It's the rate of change with respect to time of the particle's angle theta. And they do show a figure here, so let's go to that figure. Sorry about this. Here we have it. There is, let's blow this up, in fact. It's so nice. I didn't have to draw it, but I did. Okay. So here you have a particle moving along the circle of radius r, along the circle here, constant speed along that circle. That means the angle is changing at a constant speed, and the angle is omega t. The angle is omega t. Omega theta divided by t would be your omega, the constant. And with that in mind, then your y-coordinate here would be your r cosine omega t. Your x-coordinate would be r times the sine of omega t. This is your angle theta, which is omega t. Any questions? The velocity has, okay, the angular, okay, so moving along a circle with angular velocity omega, we said that, has a speed of absolute value omega r. Now, what does that come from? Well, omega is theta over t, right? So that's the time rate of change for a constant angular velocity. The angle is changing at a constant rate. That would be omega over t. Now, the arc length cut by that would be how far it travels, right? And that arc length is usually s. If I go to right on here, of course, it's going to shrink. So s, remember the formula for s? Okay, yeah, no integral involved, just the arc length of a circle. It's, remember how we define a radian? The ratio of arc length to radius. So arc length would be theta times the radius. So this would be r theta. So arc, as long as theta is measured in what? Two ways you can measure it. Theta, your angle. Degrees are radians. This formula is only good for radians. So that's how we define radian. Radian is a ratio of arc length to radius, so therefore S is equal to R times theta, when theta, that is a theta. It's a pretty ugly theta, but give me a break, okay? Complaining so badly. Okay. Now, that is your distance traveled. Well, the speed would be the time rate of change of that, wouldn't it? Okay? And this is constant over time, so distance divided by time, that would be r theta, and this would be velocity, v, or speed, absolute value. Anyway, speed is always positive. Well, but didn't we just say, yuck, I've covered it. Maybe we didn't, we said it somewhere. I thought we said it. Yeah, it's under here. Let me, yuck. No. There we go, finally. Okay, yeah, there we have it. Okay, put the T here. Okay, but we said right here that omega is equal to theta over T, right? Here is theta over T, so this is R omega, or at least the absolute value of that. So that's how your velocity or speed, absolute value of velocity, would be absolute value of R omega. They didn't go into gory detail on that, but that's how you get it. Okay, so let's do example 5. Calculate the speed of the circular path of radius r, this picture here, and angular velocity omega, this picture here. Calculate the speed of the circular path of radius r and angular velocity omega. What is the speed if r is equal to 3 and omega equal 4 radians per second? All right. What they're asking you to do is go back in time. I know it was a long time ago, like maybe Monday, when we had this. The speed is the s dt, which is the square root of x prime squared plus y prime squared. Again, I really don't care for the square being at the t, though it's okay. I think it would make more sense if you put it in brackets in there. But when I typed the test, they had it the same way, and I didn't want to do extra typing, so I typed it the same ways. Since y'all are used to it this way, so this is what we're going to be doing, is finding this speed, and we, goodness, yeah, okay, I'd written on the previous one, that's right. All right, remember what we had. We just said the C of t is equal to r cosine omega t, r sine omega t. What's this r cosine omega t? What could we call that too? X. That's your x as a function of t, and this is your y as a function of t. Okay? And what we just said was your speed, ds dt, which we don't know s, so we can't do that one. We could figure it out. But we just said this is the square root of, tell me what that was again? D by dt, is that what you said? Yeah. X prime squared plus y prime squared. Okay, I'm just leaving out some of the odd t's in there. So what was one of the first things we're going to have to do? Figure out what? What? Yeah, x prime. X prime of t would then be equal to, there it is, r minus sine omega t with one little thing, chain rule, another omega out there, right? And let's do the same thing here. Your y prime of t, because we need that as well, y prime of t is, yuck, r omega cosine omega t. Positive in that case. But we also have to square both of those, so x prime squared is squared omega squared sine squared omega t. And your y prime squared is r squared omega squared cosine squared omega t. All right. Now we have to add those together. So let's do this one plus that one. What does that give us? Factoring out what we can. Okay, since it's under the square root, I hope this isn't skipping too many steps. You factor out an r squared. Under the square root, that comes out as an r, right? Also factor out an omega squared from both of those. That's under the square root. Pull it out, and that's just an omega. And then what do we have left? The square root of sine squared omega t plus cosine squared omega t. And any idea what that could be? One, exactly. This is 1. So we just found out that is indeed r omega, which is what we had before. And of course, it's the positive, so even if r or omega were negative, that would be the absolute value. Okay? So, and r can't be negative, of course, so omega r or r omega, it doesn't matter which. Okay. Now, that was the first part. Calculate the speed of the circular path of radius r, angular velocity omega. That's all they say. That is the speed. R times the absolute value of omega. They put absolute value of omega times r. Now, what they ask, secondly, what is the speed if r is equal to 3? And that's in meters. And omega is 4 radians per second. And this isn't really a unit, but I'll put it this way. A radian is a unit, it's a ratio, okay, of two values with the same dimension. So it usually is not a unit, but just to humor them, we'll do that. So then what is your speed, ds dt, for this one? Pretty easy to do. 12 units meters per second, because radian really isn't a unit. It's just a ratio of two lengths having the same unit, so it doesn't have any units. But we write it there so you get the concept you're talking about, an angular velocity. Okay? That's it. That's pretty simple too, right? Now, Consider the surface obtained, boy, jumping a new rabbit here, by rotating a parametric curve. Let's go on and go to a clean page here. Yeah, here's a good page to use. Consider a surface obtained by rotating a parametric curve, C of t is equal to x of t, y of t. By the way, I've just been noticing we're staying in 2 dimensions now, but all this can be extended to 3 dimensions, okay? Everything they've done so far has been 2-dimensional, so I'm happy with it. I'm okay with it. Easier to graph that way if you have to, okay? Rather have them graph it. So here is a surface obtained by rotating a parametric curve about the x-axis, okay? So let's just say here is that curve, okay? Or you could put a loop-de-loop in it. I don't care what you do to it. Some curve up there. You rotate that about the x-axis, okay? And you get a curve that does something like that. Obviously, mine's not drawn to scale. But you rotate the whole thing around that, okay? Around the x-axis, okay? Now, the surface area is given by equation 4 in the next theorem, which is right here. It can be derived in much the same way as the formula for the surface of revolution of the graph y is equal to f of x way back in section 8.1, last term. In this theorem, we assume that y of t is always greater than or equal to 0, which I drew that way. So the parametric curve lies above the x-axis, and the x of t is increasing, so the curve does not reverse directions. So I said you could put a loop-de-loop in it, but it would really screw things up, so have it increasing in x, okay? Now, we'll leave that alone for now. So here is the theorem. I'll expand on this. My picture isn't all that great anyway. But let's blow this up appropriately. All right. So let C of t be some x of t, y of t. I have it written out. Where y of t is always greater than or equal to 0. You don't have it crossing the x-axis anywhere. You could touch it, but not cross it. X of t is increasing, so you don't have any backing up on itself. Y of t could be going up and down. X of t, though, is increasing. X prime of t and y prime of t are both continuous. Okay? Need to have those both continuous. First derivatives are continuous for both x and y. Only the x has to be increasing, so that's always positive. The y can be positive or negative. Then, the surface area obtained by rotating that C of t around the x-axis for a less than or equal to t less than or equal to b. That's why I was sort of puzzling with how I should draw my figure there. What I did was the xy axis, but the curve is a function of t, and t equal a was one end and t equal b was the other end. Didn't matter what the x's were for that set. So here is that equation. And I hope you remember this from before. 2 pi. Now if you need a little reminder of where that comes from, basically what we're going to do here is this. We're going to take some little, I forgot. All right. We're going to take some little arc length here, and this is going to be our dt. Okay? That's not an arc length, that's a change of the variable. Okay? So, what we've got here is this little segment here, represented by that dt, is going to go around the thing. Well, and that little segment's going all the way around, and that's really a circular thing there, okay? And what is the area of that little strip that goes around like that, okay? Now, dt isn't what it is, but it's represented by dt. Well, the area of that little strip is going to be 2 pi times the radius. Well, what is the radius? The radius is the y value, right? This is x, that's y. That's the y value around the x-axis. The radius is y of t. So 2 pi r, 2 pi y, that's going to be the length that goes around there. Okay? Well, what's the thickness of that? Well, the thickness is the arc length, which was the square root of x prime t squared plus y prime t times dt. That's what you, because you see this thing right here was your speed. Speed times time is length. And there's your time, delta t, if you're thinking in terms of time. So this would then be this, that. So actually that little strip there, represented by dt, but it's really this thing right here. That is the thickness of that little strip. And then you integrate that from t equal a, which is here, t equal a. This is x, and this is your y, and up here is where t is equal to b. So when you integrate that strip around this circumference, that gives you your surface area. Integrate it from a to b. That's it. That should feel pretty reasonable. Okay? Does it? All right. Now, with that in mind, let's do example 6. All right. I don't know if blowing it up will help any, but maybe it'll make it go away. Boom, we blew it up. No. All right. Here, ooh. I just about, oh, okay. We're not doing that one. That was in the old text. This is in our text. It looks a little backward from this, so don't sweat this figure. Look at the one in the book. So I'll get rid of this one. We're not doing that, okay? Doing the one in the book, which basically kind of looks like this. It's the megaphone going the other direction, okay? And here, our C of t is t cubed, okay? Now, first, does this meet the criteria for the last theorem? The last theorem said it has to always be positive. Well, if you stay in the first quadrant, which we are, we're going from 0 to 1, 0 less than t less than 1. Oh, they have equal signs there. Okay, it doesn't matter. So yes, t is always positive. So the first value is never negative. It could be 0 at 0. And the second is always positive. So, yeah, we are in the first quadrant, always positive, and the x is increasing, x of t being t, increasing in that first quadrant, 0 to 1. So that fits, okay? Now, calculate the surface area of the surface obtained by rotating this parametric curve around the x-axis for t 0 less than or equal to t less than or equal to 1. Surface area appears in the figure in the book, kind of represented here, okay? Okay. So, what would be that surface area? Remember what the formula was? 2 pi times the integral from 0 to 1, because this is a dt we're going to have here. So that's going from 0 to 1. Your y, which was your t cubed here, because 2 pi y, that's going to be this. You're rotating this around the x-axis, so you're rotating this y around. The y is your t cubed. Rotating that around there, that's 2 pi y. Okay? So there's there is the circumference part, and then the interval part is your square root. And what goes under that square root? Okay, we've got to figure out what x prime is. X prime is 1. So x prime squared is 1. Okay, got this down. Now, what about your y prime? A little louder. 3t squared. And your y prime squared then would be 9t to the fourth. Oh, what a lovely number. Okay. And so what we have here is your x prime squared, 1, plus your y prime squared, 9t to the fourth. Oh, I'm loving this, aren't you? Isn't that such a perfect little integral to do? But really, it's not that bad. What do you notice here? Okay, sometimes we call that substitution, right? Yes, all right. So let's let, did you say u? I thought you did. Okay, let u equal, what's inside that? 1 plus 9t to the fourth. Then what's the next thing we do? Then du is equal to 36t cubed, right? All right, we don't have a 36t cubed. We have a, I forgot, dt. It's a differential. du is equal to 36t cubed dt. We don't have a 36t. We have just a t cubed dt. So let's divide both sides of this by 36. Okay? Now we have t cubed dt. So let's rewrite this. Our surface area is equal to 2 pi times the integral. Oh, we've changed our variables, haven't we? Okay, we were going for t 0 to 1. So when t is equal to 0, what's your u? 1. Perfect. When t is equal to 1, what's your u? 10. So now we're going 1 to 10. And we've got what our t cubed dt is now du. This part is now your du over 36. Or you can wipe out the 2 here and make it 18. Right? Yeah. Okay. Catch what we did there? Okay. So the du was du over 36 was our t cubed dt. So we got that taken care of. And then what's the rest of it? U to the 1/2 power. And I far prefer integrating that than square roots. Just so much easier to do. So I think we can do that then. We've got pi over 18 out front. Nice round number. And what's the antiderivative of u to the 1/2? U to the 3/2 times 2 over 3. Okay? Well, I'm going to wipe out this 2 with the 3, this and make a 9. So that now gives me pi over 27. I'm going to take this on the outside too. So that's pi 27ths. We're going to evaluate this from Marcus being here. We wouldn't have evaluated it if he hadn't come in. Okay? All right. So all we need is faith, and we'll have 100% attendance again today. Let's see, did my last class have that? Yes. This morning class, 100%. Second class, 100%. One person, and we'll have it today too. Evaluating this from 1 to 10. Okay? Now, again, this is a pi 27ths. We're doing the example 6 at the top of page 594. The last thing we're going to do in 11.2. Well, not quite, but close to it. So that's pi 27ths out front. And then, a real pretty thing, what is in your parentheses? Basically, it's the square root of 1,000, isn't it? Now, you could write that as 10 root 10. Maybe that would be the easier thing to do. Okay. That's 1,000, isn't it? U cubed would be, 10 cubed would be 10 times 10 times 10. Take the square root of that. 10 times 10 is 100. Take the square root of that is 10 times root 10. Okay. Minus, ooh. minus, the next part's pretty easy. What? 1. Okay, good. All right, that is our answer, whatever that is. You can pull out your calculators and actually calculate it and see what you get. We got pi 27ths. They left it as 10 to the 3/2 power. Yeah, it's fine if you wanted to do that. I wrote it as square 10 root 10 minus 1. 3.1, right? Yeah, that's what we look at. Good for that. Okay, that's approximately 3.5631. Yeah. I don't know where they got all those digits, but that's fine. All right, makes sense? Not an unreasonable formula to use, and it's not. If you remember that the square root of x prime squared plus y prime squared is your speed, okay? And speed times time, in this case delta t, that's your distance. Then the distance times your circumference, that's your area. And that gives you basically the formula. All right. Y'all want to do preliminary questions or not? Yeah, okay, let's do it. I think that's the last slide, so what I'll do is clear the slide. Okay, and we'll use this. We're not using that thing, fortunately, because I don't really care for hyperbolics very much at all. Now, watch, all of you wind up having to use them all the time, and you'll be cursing me for not teaching them to you, but they're just, all the times I've had since I took calculus, I can't ever remember really using a hyperbolic anywhere except a made-up hyperbolic problem. You know, I'm sure there's some application somewhere out there. I just haven't run into it, so I think why go through all that? You look it up in a table if you need it. Okay, that's what I do with most of them anyway. So let's see. Preliminary question: what is the definition of arc length? Okay, you don't even have to flip back. Look at the summary right above that question. That's exactly what we had. The arc length was the integral of the square root of x prime squared plus y prime squared dt. Okay, from A to B. That was your arc length, remember, that we had. Multiply that by your circumference, that's how you get your surface area. So you see the very thing down there, all you're doing is multiplying that arc length by, and you throw the y in there because that's part function of t2, 2 pi y. And then you have surface area. So those two are pretty tied up together. Number 2, can the distance traveled by a particle ever be less than its displacement? No. Displacement is shortest distance between the two, the beginning and ending point. The distance traveled, you can't ever travel any shorter distance than that and get from there to here. Okay? That is the shortest distance. So no. Distance traveled by a particle ever be less than the displacement? No. When are they equal? Traveling along the line that connects the 2 points. Then they are equal. Number 3, what is the interpretation of the square root of x prime squared plus y prime squared for a particle following a trajectory xy? Just that radical. What is that, the interpretation of that? Let your eyes float up just a short ways. What do you see? Speed. It's the speed at any time t. Right? Okay. Number 4. A particle travels along a path from 0, 0 to 3, 4. Okay? What is this? Is the displacement? What would that be? Zero, zero to here. What is its displacement? Now, we don't know it went along that path, but what is its displacement? Say again? I can't hear. Okay. Wouldn't that be, what do you want to name that distance? A? I don't like A. Huh? X? I don't like X. Okay. I don't have any problem with W. Okay. Now, how could we find the length of W? Its name, Pythagoras, ring the bell. Oh. How do we get that? Plus. Huh? Say that? Okay. W squared equal, and you said 3 squared plus 4 squared? Is that what you said? I was trying to listen in. Yes. Okay, and that was 9 plus 16, 25. If W squared is 25, W is 5. Its displacement is 5. The good old 3, 4, 5 triangle you're all really familiar with, right? Okay. So we got the displacement. Can the distance traveled be determined from the information given? No, it doesn't say how it got there. It went straight line, yeah, that's it. If it wandered around here, it went a lot further than that. But it didn't tell us anything about the path, so we don't know what distance it traveled. So that part's no. Okay. Let's just check up on our answers here, which I'm certain are right, because you agreed with them, because I'm browbeating you. No, I didn't say that, did I? Okay. 11.2, the arc length, which in the back of the book, they really blew this one. They put capital S, and that should be little s. Little s is arc length, capital S is surface area. They put capital S for surface area, but gave the formula for arc length. The second one is no, and we said that, and then said they're equal when the curves traced by C of t is the line segment from the initial point to the final point, the straight line path. We said that. And number 3, we said what is the interpretation of that? We said the speed at time t. And then the displacement was 5, and no, whatever the question was, I forgot now. Can the distance traveled be determined? No, we don't have enough information. So let's look at 5. A particle traverses the parabola y is equal to x squared, okay, with a constant speed 3 centimeters per second. Okay, that's its constant speed. What is the distance traveled during the first minute? Man. Hint, only simple computation is necessary. Okay? What you reckon that simple computation is? Second? 3 times 60, exactly. 60 seconds in a minute. Okay? So multiply, let's see. Yeah, and that would give you distance in 3 minutes. All right, is that what it asks? Oh, first minute. Seconds in a minute, and you traveled 1 minute. Centimeters in a minute. If you multiply, okay, let me get this right. 3 centimeters per second times 60 seconds per minute. That gives you 180, right, centimeters per minute. That's how far it traveled in the first minute. By that, 11.2, 180 centimeters in the first minute. Absolutely. Number 6. Let's clear this out of the way. Okay. If the straight line segment given by C of t is equal to 3t, 3 comma t, okay? For 0 less than t less than 2, they're equal to 2, I would say that, is rotated around the x-axis, okay? Okay, that's rotated around the x-axis. What surface area results? Okay. It might be useful to try to draw that in here. Okay. Um, 0 less than t is less than 2. So where are we at t equals 0? Three, 0, right? Where are we at t is equal to 1, say? 3, 1. Now, I'm not going to do their scale, I'm going to do my scale. Okay? That would be here. And t is equal to 2, 3, 2, right? That's the path. Okay? That's what I was thinking it was. I needed to draw it to confirm that. Rotate that about the x-axis. There, I've done it. Okay? What surface area results? A little louder. Okay. Okay, but the surface area means the outside area here, not the surface here. But the thickness is here. That's a vertical line. It creates no surface area around. We're not saying it makes a drum. We're saying there's nothing there. Unless I'm misreading the problem, I think it's 0. Let me see it. No. I must be misreading the problem. What's that? Yeah, but if we tried the formula, okay, let's do it. Let's do the formula and see what we get. Okay. We're using the formula. Maybe I'm missing something here. This is capital S. I like to say SA so we don't get it confused. Okay. Unlike the book did. It's 2 pi times the integral from 0 to 2. What's your y? T. Times the square root of 0. About 1 squared is 1. So that would be, yep, this is going to give you exactly what they say. 2 pi times, what's the antiderivative of t? T squared over 2, evaluated from 0 to 2, and that would be 2 pi times 4 divided by 2, which is 2 minus 0, 4 pi. And that's exactly what they get. Now, what's that?
Since you're going from 0 to 2, your radius is 2, and it's a circle, so you multiply 2 pi times 2.
Okay, yeah, you may be right. That may be covering, that may be this, the surface of that. I guess that's what you are, because you are, yeah. You're putting the skin on the end of this rock. That's what you're doing. And so what you said was right. That would be pi r squared, where your r was 2. So pi r squared, where r is 2, is 4 pi. You're right. It was that. So you are putting a skin on it, because you're starting here and going up here. So you're putting, there's no part here. Okay? There's no thickness there, so it's just the area of that circle. So you're right. 4 pi. Without having to do the formula. But the formula did do it. Okay. Exercises. Any of the odds 1 through 9. Either 11 or 13, or both if you choose. Any of the odds 15 through 19. Any of the odds, no, either 21 or 23, or both. I'll let you choose. Then either 25 or 27, or both. Then 29, do 29. It's a new term there. It's called an involute of a circle. I'll let you figure that out. There's a picture there. And then any of the odds 31 to 37. And that's it. Now, further insights and challenges, there's something called the trochoid talked about. If you find that of particular interest to you, knock yourself out if you want to write a paper on it or whatever. However, you also have Newton's laws of motion and gravity, which most of you know already. You also have something on Kepler's third law. So Newton, Kepler, Newton's laws of motion and Newton's law of gravity, Kepler's law of planetary motion. There's 3 of them, and this is the third one. So if you want to do on any of those would be legitimate. All right, I'm not going to take the time to do anything on 11, 3, 4, or 5. 11, 3 is polar coordinates. If you think you'll need those at any time in your career, review that section. Then 11.4 is area and arc length in polar coordinates, which is pretty short, and it's basically doing the same thing we just did, only in arc length. And then 11.5 are your conic sections, which wouldn't be a bad thing to look at because section 12.6 is going to refer to those. So I would definitely, in fact, since we're going to go there, let me go on and eliminate this, and let's go and just look at this. That was what, 11.5. This is worth the effort. I'm not going to test you on this, but you're going to see it later, so might as well get used to it now. Okay. As I said before, everything we've been doing so far has been two-dimensional. Everything in 11.1 and 11.2 were two-dimensional. And for some reason, 11.5 is having a hard time loading. I don't know why. Let me try it again. Okay. I'm going to close this, I think. Okay, let me try it again now. There we go. All right. And we'll start from the first slide. Have y'all hit this ever before? Whoa. Okay. You probably have heard the term conic sections, but have you really studied them? Any of you? Okay. Most of the time they're kind of ignored. Here's where they come from. A cone, technically, is not just one filter paper, but 2 in the end. That's a cone, the whole thing. Okay? Now, and this is a right circular cone. Okay? So if you cut that cone anywhere here, like there or there, perpendicular to the XY axis, or in the plane that's perpendicular to the axis of that cone, you're going to get a circle. If it's a right circular cone, that's going to give you a circle. However, if you slice through an area of the cone, not perpendicular to the axis, but at some angle not 90 degrees to the axis, you're going to get an ellipse. If you slice through the bottom part of a cone without, or top part, either one, without going all the way to the other side, you get a parabola. And if you slice that cone with a plane that's parallel to the axis, then you get an hyperbola. The hyperbola always comes in pairs. A circle is, of course, a circle. An ellipse is an elongated circle with a major axis and a minor axis, and a parabola only is a singular curve. So all these things that perhaps you have studied and perhaps not, they all come out of cones. So they call them conic sections. Okay. Now, that's sort of interesting, neat, wow, ooh-wah, you know. But what you do with them, I'm not going into gory detail on this. They do give a formula here for, and this is for an ellipse, okay? And they haven't given you what these things are, but I'll tell you, F1 is your one focus and F2 is another focus, and I'll tell you what that means in just a second. I think when you see this, oh man, they skipped the figure. That's not nice. Ah, there's the figure. Boy, this is way out of order. Okay, maybe the old book didn't do it this way. Okay. Is this the right order for yours? Okay. So the new book has changed the order on this, and I think the new edition, I think I like it maybe a little bit better. Okay. Can't get all this on here, but let's get a parabola. I mean, an ellipse has two foci, one to the right and one to the left. And the ellipse consists of all points P, such that the distance from P to the first focus plus the distance P to the second focus is always constant. Okay, so you see distance here P. This distance to focus 1 plus the distance to focus 2 is a certain value. You swing around here. Here's the distance perfect to focus 1. There's the distance to focus 2. Guess what? It's not proven, but that is the same value. This one got longer and this one got shorter. Okay? You go up here, and this one's getting longer still. This one's getting shorter still. When you get over here, it's obviously the same distance as that. And by the way, we can figure out what that constant is. The constant is the distance from focus 1 to the edge here plus focus 2 to the edge there. So it's the distance between focus 1 and focus 2 plus twice that distance. One way to look at it. Okay. Now, that's what defines an ellipse. How do you draw one of these? Take 2 pens and a board, piece of paper, whatever. Take a string of a certain length that has to be longer than that length there. And take your pencil, and if it's attached there, do it like this, and you get an ellipse. That's a constant length. Okay. And basically, Kepler's first law, I believe it was, says all the planets revolve around the sun in elliptical pattern with the sun being one focus. He doesn't, as far as I know, define what the other focus is, but they're always elliptical. Most of them are very close to circular. One is awfully close to circular. All the others are just ever so slightly elliptical. Okay. Now, from that, you can do these distances and do some manipulations with it. And here's one definition for you. The distance from the center to the edge of the ellipse. If the ellipse is centered this way and that way on the origin, this distance here is little a. And that's called the major axis or the semi-major axis. And the shorter one is the semi-minor axis. That would be B, 0B. And with that in mind, x over a squared plus y over b squared is equal to 1. Now, does that in any way look like any other formula you're used to? If the a's and b's were equal, can I give it a different symbol? Maybe r. Then x over r squared plus y over r squared, it would also equal 1. But if the semi-major axis is equal to the semi-minor axis, guess what we got? A circle. And then we can square this x squared over r squared plus y squared over r squared, multiply both sides of r squared, x squared plus y squared r squared. So yes, the only difference here is your a and b are different lengths for this, an ellipse. And by the way, a circle is an ellipse. It's just A and B are equal for it. So, all right. So there is the equation for ellipse. That's the reason I showed you this so far. You might say, why are we going over that? We're going to need that in a little over a week, probably. Probably a good deal over a week. Okay, they do some calculations here. We won't do all that, but going back and seeing that. Okay, so here is your definition, or theorem here, they call it, which is awfully close to a definition. An ellipse in standard position, that's with the center at the origin, as long as A is greater than B is greater than 0. Now they don't say, well, yeah, they put A's with the X's, so this is always going to be ellipse. The football is lying along the x-axis, okay. It's not a football yet, but it would be. Okay, and set C to be the square root of a squared minus b squared. We haven't done that yet, so don't sweat with that. The ellipse, which is PF1 plus PF2, equal to 2a. There's what that constant was. What did they call it before? A. There is now 2a. With foci at C0 and minus C0. Those are your two foci. And that C is related to the A's and B's. A's always being greater than B's, and that would be that. Furthermore, the ellipse has a semi-major axis A, semi-minor axis B. The focal vertices are plus or minus A, 0 plus 0 plus or minus B. Now, if B were greater than A, just turn it up like this. On the y-axis is the long axis, and then the equation to find now your C is the square root of b squared minus a squared, because it's always the longer minus the shorter. Get the same thing, the same formula here, it's just that then the A would be less than B, so B would be the semi-major axis. Okay. You don't even need to know all this, but that's the equation of an ellipse. Okay. Here's pictures of an ellipse. I won't do much else with it. If you know the semi-major axis is 6 and minor axis is 5, fill in the blank. Okay. Now, what if the difference between the point and the two foci is either plus or minus constant k. What do we have then? Okay, what we have then is a hyperbola. Now, this isn't quite fair. In fact, it's not fair at all, but it's almost like, it's not the same, but it's almost like taking the ellipse and flipping it over, you know. That won't work, but it almost gives you that impression, okay? Now, always A is positive and B is positive. And C now is not the square root of their difference, it's the square root of their sum, okay? The hyperbola P F1 minus P F2 with an ellipse is a plus. And this is equal to plus or minus 2A. Remember our constant before was 2A? This is 2A. With foci, F1 is at C0, F2 is at minus C0. Same as before except the definition of C. But this time, the things are going like this. Okay? Not going together, but going apart. And that's the equation for a hyperbola. And again, this may not seem important now. It's just a bunch of letters and numbers. By the way, this is sometimes called analytic geometry, if you want to put a name on it, study of conic sections. It looks a lot like the ellipse. The only difference is it's a minus sign rather than a plus sign. Okay? Now, boy, this is sort of jumping all over the place here. Of course, I'm not carefully following the book. But seems like we should have done this before we got into ellipses. Okay? Even mentioned hyperbole. Now we're taking an ellipse and translating it. What you have now is if you're translating from the origin to a point 6, 7, the x has shifted 6 units, so that's x minus 6. Remember, anything you do with it, you're going in the opposite direction. But now you use that same rule for y minus 7 squared, and other than that, it's the same. Now here you're assuming major axis is on y, so the 5 is there, the 3 is here. So that's how you do an ellipse who has been a translation of an ellipse from the origin to the center somewhere else. It just changes the x and y's up there. Okay. Why they didn't do this earlier, I don't know, before they got into hyperbole. Oh, I said I was going to give you the test, but I forgot to. Let me do that before I forget. I guess I was sort of in the back of my mind hoping our fourth student would come in. Do y'all see faith at all? Do you have any in the class? If you listen to this, you can hear about the test. Now, what's that? Yeah, this is first two sections of 10, first two sections of 11. In fact, I'll roughly give you the thing. 1 and 2 are basically from 10-1. 3, 4, and 5, I think, are from 10-2, yeah. Okay? 6, 7, and 8 are from 11-1, and 9 and 10 are from 11-2, I think. That's my memory when I was making them up. Okay. And we'll notice I gave you that formula. I didn't realize we were going to be harping on it so much today. I could have saved myself a lot of typing. But for you, I don't mind. It wore out my fingers, but I don't mind at all. Okay. Just kidding. Okay. Now, sorry, I just happened to my eye catch the test up there and said, I never gave those out. Okay. Why they did it, that figure then, I don't know. Here is your figure of an ellipse. Okay? This is, hyperbola. Here is your F1, there's your F2. This is C0 minus C0. Okay. Again, what they said, the difference between this distance and that distance is equal to 1. Whereas before, is a constant. Whereas before, it was a sum for a hyperbola. I keep saying back. For an ellipse, it was a sum, here it's a difference. Okay? And that's the, and then they call that the conjugate axis because the same thing's happening on the right is happening on the left. Now, if you did it the other way, you could have the conjugate axis, the hyperbola could be going along the y-axis. Okay. The focal axis is the one with the two foci on it. The conjugate axis is the perpendicular one to that. Not that you need to know that much. Okay. This is that same hyperbola, it looks like, but now they're illustrating the values. The A is obviously still, in this case, the distance to the curve from, if it's centered at the origin, the distance from the origin. So the curve intersects A0 minus A0. Now the B is not nearly as easy to figure out, okay? But notice how this is where my analogy of the inverted ellipse falls apart. Because an ellipse, they're coming together here. In a hyperbola, the shape is like that, but they're not coming together. They're going off along asymptotes, but these are slant asymptotes, okay? And what is the slope of that slant asymptote? B over A. See, B hasn't entered the picture anywhere here except in the formula. That's what it stands for. That's where it's not really a foci, intersection point, but if you went up plus B and down here minus B, and the perpendicular from A's, from where it does cross, then that forms the asymptotes that the hyperbola is approaching everywhere. Okay? So that's where the B. It's sort of an imaginary point. There's nothing there. This is where the A is where the hyperbola crosses the focal axis there in minus A. B is sort of an imaginary point there that the box there defines the slope of the asymptotes. So, for whatever that's worth. And then the C, remember, with the square root of A squared plus B squared. So, that doesn't look right. Square root of A squared plus B squared would be this, and that looks like that's not drawn well, okay? It doesn't look like C. But I'm not going to worry about that now. Okay, now, here's another rather strange situation for a conic section. Here, some point to the focal point is equal to some point to a line. That's what the D stands for. What in the world is that talking about? These slides are so badly out of order. I'm sorry. This is going back to something like we just did before. Sorry, this is jumping all over the place. This is the other rendition of a hyperbola. The formula that looks more like what we were doing is divide all three terms on both sides by 36, and this would be 9 over 36 is 1 over 4, so it's 1 over 2 squared, so 2 would be this, minus 1 over 3 squared, so 3 would be this or that, and that would be equal to 1. That's the form we're used to seeing. There's your hyperbola with a minus sign. If that had been a plus sign, that would have been an ellipse like this. It's not, it's an hyperbola. Now, this is saying that the square root of 2 squared plus 3 squared, 4 plus 9 would be 13, square root of 13. Well, let's see if this is drawn a little better. That link should, yeah, this one I can buy that. That looks good. Yeah, that is that. This one over here, they just don't have the focus in the right place. I mean, the focus in the right place. Because there's no way, I don't think, that would be right. The focus should be out there a little bit. C has to be that hypotenuse there. Okay. But that's neither here nor there. So, enough said there, hopefully. Here's, this is the figure that went with that last formula. The PF, the distance from a focus, is equal to the distance from some line. Okay? This line, okay. That's the axis. This distance to the focus is equal to that distance to the line. Well, that sure doesn't look right, does it? Yeah, I guess it is. Okay. And anywhere, obviously, focus is the same distances from that line above and below. It has to be there. And then here, and here, and here, and here. So it's always that. And that line is called the directrix. Okay? That D, they wrote it a funny looking script D, and that's called the directrix. And that's Y is equal to minus C if the focus is at 0 C and the vertex at the origin. So that's the parabola with the focus at 0 C, directrix of Y equal minus C. So that's your equation for that. Well, I haven't seen an equation yet. That's just a picture for it. What they've done here is shifted. What they've done, they've shifted the x to the right 2. They've also shrunk it by a factor of 1/8, okay? And they shifted up 8. Should have, oh yeah, okay, I'm sorry, I was looking at it. Here's the axes, okay? And that went up, the right 2 and up 8, yeah. So just like we saw before, the thing that follows the x is the x minus h, y minus k, where hk is the new, in this case, your new vertex. Okay. And if everything else stays the same, then your directrix is that. So that shows both a vertical shrink and a horizontal shift, vertical and horizontal shift. I should have blown that up, sorry. Now, this is not, we won't find this very useful in what we do later, this particular formula here. It's okay, it's true, but this isn't how, that's a little bit how it's going to look. The focus at 0 C, directrix is y equal minus C. Then y is equal 1 over 4c times x squared. That's how your parabola always looks. Okay? Vertex is located at the origin. The parabola opens upward if c is positive, opens downward if c is negative. Okay? Because if it's negative, you just flip these two. Focus is minus it, and hang on to that. Y is by itself on one side, x squared is on the other side. You will see things that look like that. Okay? Now, I don't think the rest of this is really all that important, but in case you ever need it, you've seen it at least once. The eccentricity, E. Now, lots of things are called E. The base of the natural number system is called E. This is not that E. Efficiency in physics or mechanics and things like that. That's called E. This is not that E. Okay, so lots of things are called E. Here it's the eccentricity. Okay, and that's your ratio of the C over A. Now remember, in an ellipse, the C is less than A. In a hyperbola, C is outside or greater than A. So an ellipse has eccentricity between 0 and 1. It could be 0. If it's 0, what kind of ellipse is that? Circle. Okay? Otherwise, it will be between 0 and 1. But never 1. Hyperbola has an eccentricity greater than 1, so C is greater than A. Okay. Now, I think this is a summary slide. Can I get it all on there? Oh, yes. Barely. Okay. And by the way, what we didn't mention is the eccentricity for a parabola is 1. Okay? I was going to say we didn't mention that, but now they do. So a circle is eccentricity of 0, ellipse is between 0 and 1, parabola is equal to 1, hyperbola is greater than 1. Okay? As the ellipse does flatten as E approaches 1. Because E is 0 would be a circle, and just slightly off a circle would just be slightly bulging at the equator, and then more and more and more until it flattens out as E approaches 1. And at that point, it becomes hyperbola, which doesn't make sort of sense according to the pictures here. But then as you go further from 1, just slightly more than 1, it's sort of like that line starts opening up outward. You know, it flattens, and then inverts and starts opening the other way. So your eccentricity, the larger the eccentricity, the more linear that hyperbola becomes. Okay. So here's another way to express PF is equal to EPD. With E as 1, that gives you exactly a parabola. Okay? But now they're saying you can write them all that way. So we're not getting into that. Then your directress is on the outside. And your eccentricity is involved with it. So not going to fiddle with that. And here your directrix is on the inside. But you see, you still got that same formula works for all of them. And that's why the conic section, really defines them all. And then that determines where the signs are, plus, minus, and go back and forth. This is a lot more than what we'll need later on. I just want you to be used to it. And then this is the situation that you would have for a parabola where the D is equal to 1. Goodness. They just keep on trucking, don't they? By the way, that was a pretty interesting thing there. This is, you know what shape that disc is? Parabola. Why a parabola? Because the characteristics of parabola, all the rays coming in, and if this is coming from a satellite or something way in outer space or anywhere, those are awfully close to parallel rays coming in. You're not close enough to have any curvature. You're so far away. So they come in parallel, they reflect toward the focus. That's why we call it the focus. receiving unit is at the focus. Your parabola is focused at the focus, so it shoots at picking up signals from that geocentric satellite that's up there, and that's where you get your satellite signals for your dish TV or whatever, direct TV, all those discs that you have, that's exactly what they are. Now, let's take it and turn it the other way. Let's say we put a light here, and the light goes out and hits the parabolic mirror. It goes out parallel. Where would you find mirrors like that? What's that?
Like a stage or something like that.
I couldn't hear.
Stage.
Stage? Oh, you mean light, yeah, lighting. You're in theater, aren't you? I see what you're talking about. Okay, yes, a flashlight. Parabolic mirror, almost a parallel beam of light going out. Put the light bulb at the focus of that parabola, you get a beam of light. Your headlamps on your car, you know the shape of that? Put the bulb right in the focus, and you're almost showing out. And of course, it's not exact because your bulb is not a point source. So you get some spread, but you pretty much got it. So all those mirrors are parabolic mirrors. Okay. And when you're trying to catch rays from the sun to convert to, say, heat, and Georgia Tech had one of these decades ago, had a long parabolic mirror type thing that focused the sunlight onto a tube running in. It was a parabola that was parallel all the way. A pipe running down, and the liquid in the pipe would get heated because all the rays focus on that, and that's how they generated heat. It was a prototype, and sure enough, they could make some pretty hot water with that. And you could get it hot enough to make steam and run a turbine with that. No fossil fuels, okay. But a very big mirror. And you need, it only works in the daylight, sunny days. Okay, so there are some disadvantages. Okay, while we had it there. The dome in the U.S. Capitol building, parabolic dome, okay? It focuses all the sound to one place, and you have some places along there. And here is, obviously, John Quincy Adams understood physics fairly well, or maybe someone told him. There are things like they call whisper chambers, and if you've ever been in the Capitol building, they'll probably point these out to you. If you stand there, it might drive you nuts, but if there's a lot of people in there, you can, and they said that John Quincy Adams would locate one of the foci in order to eavesdrop on conversations taking place at the other focus. So if you could get someone to talk one place, you get around to the opposite side and listen in, he could hear exactly what they were saying across the floor there. Again, parabolic shapes. Okay, now, you'll see a little bit of this in chapter 12. What we have here, when you have forms that are like this, basically what we do is when you have these cross terms, that means your axis is rotated in some form or another. That's what I mean by the cross terms. These terms translate. Your x and y terms along with these translate, and these rotate your axis. And if you were to complete the square with these things and stuff, you wind up with a number here, wind up moving that to the other side, and then you determine whether you have a ellipse shape, a parabola shape, a parabola shape, or what shape. Okay. But we won't go there. This is what I mean. This is a translation over here to 3,3 and a rotation here. You have because of this axis. and you have to deconvolute all that to get it to make sense. And when you do, you get that. We're not going to go into that kind of detail at all, but if you ever need to, that's how it's done. Okay, this is one that you have a translation but no rotation. And you notice there's no cross terms in this. You can find out where your point is here by completing the square with these two terms and with those two terms. And you see this gives you a plus x, will be here, which moves the x this way, and the minus y, which moves it up this way. And you'll wind up getting exactly that ellipse. Okay. This is talking about that rotational scheme. I'll let you, we're not going to mess with that, so we won't go into that now. That's an hyperbola that's been rotated. Okay. This is not the same d as before. This is the discriminant d, b squared minus 4ac. You've seen that before, haven't you? Please say yes. Where?
Isn't it inside the square root
Of the quadratic formula. Yeah. X equal minus b plus or minus the square root of b squared minus 4ac over 2a. Yeah. That is called your discriminant. Okay. And you use that same type thing with the a, b, and c that we were using here, and that helps you tell what's going on. We're not going to mess with that, so don't worry about it, but things that you've seen before. Okay. Oh boy, that lasted longer than I was planning it to. And that does finish. You're not responsible for what we just did there in conic sections, but just because we're going to see some of that before, again, wanted to go over that. Oh man. Leaves us 2 minutes left for chapter 12. I really thought we'd get there sooner than this. But let me at least introduce chapter 12 to you. Okay, and I'm going to try to sort of go quickly through 12. I don't do anything very quickly. And focus on the things that you need the most. And it's going to take the rest of the 2 minutes just to get this loaded. Here we go. All right, current slide. All right, and they start as always with some little picture that, oh wow, gee whiz, you know. But, now, in my text, I don't have this anymore. I have a picture of a ferrofluids, suspended magnetic things, making shapes with them. Sort of a fun thing. The curves on those shapes are, you can analyze with vector geometry. Here, in the previous edition, they talked about the recently completed Bailing, I guess, river bridge in China's Wuzhou province. A 2.25 kilometer long, that's a pretty long bridge, soaring 400 meters above the Bailing River, Bailing, however you say that. The tension in the cables and the forces on its towers are described using vectors. How is that bridge held up? Not by the sides here. That would collapse like crazy. You can fold things up and you can have little bridges in the country and stuff. They have sides like that. That's what keeps the bridge from collapsing. Can't do that with that one. What they do, all the force is on here and there, okay? And then they run those cables down from there and then suspend the bridge. That's called the suspension bridge. The Golden Gate is a Golden Gate Bridge in California, San Francisco. That's a suspension bridge. Not nearly as tall as this one, maybe actually a little longer. It seems like it is, but this is quite a feat. I know we're not covering any math here, and we're probably out of time to boot. But I just would like to ask you a question. Can you imagine working on this when you're 400 meters, that's 4 football fields plus above there, and you're out there putting these pieces into place. I can't imagine it. Not me. Okay. I'd have been hanging on to something so tight I wouldn't have been able to do anything. So it's amazing to think of. The other question is, how many people lost their lives building that? Hopefully none. But I could hardly see that happening without that. So anyway, we won't cover the first slide. We'll start, I think we've more than covered that. We'll start with 2.1. Vectors describe all the activities going on there. We'll begin there next time. Any questions? Okay. We do have class Monday. I hope y'all realize that. Even though it's President's Day and K-12 schools are out, we're not. We still have school. So. See you. Have a good weekend. And you've got a test to work on. Can you make it any better weekend than that? Fantastic. Super. All right. And technically now the test is not due until a week from today. If you need longer time, you certainly can have it. If you can finish sooner, you can. But the reason I give you at least a week is so you can always ask questions if something's not clear about it. I'll clarify anything. If you can't figure out what we're talking about, find the problem, like it in the book. I'll work any problem in the book. Okay. Good deal. Okay.